and then this is t minus t naught is delta t, delta little t. So this is delta t, so that's 1 by delta t, okay. Then I'm going to multiply the numerator by LC, and so the denominator becomes LC cubed. Okay, so that the denominator is also multiplied that way. And then I'm left with this 1 by LC square coming from here. And I'm going to multiply both sides by delta t, capital delta t. You know, why not, right? And then group things together. KLC, and I want to make sure my manipulations are correct. Okay, so KLC square, I think, is now it's fine. Okay, or LC square and then LC square. That's sorry. This is LC square, okay? So KLC square divided by one of the LCs from the delta t, and then I want to have the delta t here divided by rho c LC cube, that quantity. Or if you rearrange this, K by LC square. I'll bring the LC here. This is just pure manipulation, there is nothing to it. I just want to come up with something that makes sense physically. Divided by rho c LC cubed delta t. So this is the Fourier number. Okay, after all the manipulations have been done. Does the numerator remind you of anything? There is the thermal conductivity. L square has units of area. Delta T by LC should remind you of the temperature gradient. So the numerator quantity is actually the rate of heat transfer by conduction. The denominator quantity you see has this fraction delta T by dt, or delta T delta little t. So this is a unsteady effect, and so this is actually a volume quantity multiplied by the specific heat and density, which is mass times specific heat times dt by dt. So this is the rate of change of stored energy. So the Fourier number is a ratio of the rate of conductive heat transfer to the rate of change of the stored energy. If the Fourier number is high, the rate of conductive heat transfer is very, very high, so heat is propagating really quickly through the body, and that can happen only if the temperature gradient is approximately 0 for a finite thermal conductivity, in that sense. Okay? So Fourier number, this is a lot to digest. What I want you to take away is that I have these two creatures, Biot number, the Fourier number. The combination of these two decides whether the problem can be handled as a zero-dimensional problem or a one-dimensional problem. Okay? The Fourier number is the last line for the day, rate of conduction heat transfer divided by rate of change of stored energy, and this is inversely proportional to the thermal time constant 1 by tau. Okay? So larger the Fourier number, faster the system responds. Smaller the Fourier number, more sluggish is the system.